In this tutorial, we'll be showing how to set up a connection between a PC and an instrument, in this case a LaCroix oscilloscope, through a LAN connection. First of all, both the PCs and the scope's Ethernet adapters must be set to the correct IP addresses. From the scope menu, we click on Utilities and then Utilities Setup. We then select the Remote tab. First of all, we must ensure that the LXI control is selected, and then we can click on Network Connections. The list of Ethernet adapters opens up. We right-click and select Properties. We then deselect the Internet Protocol version 6, since this can create problems at times. We then click on Internet Protocol version 4 and on Properties. From here we can set an IP address manually for the instrument, much in the same way as we would do for a router, for instance. It doesn't matter what values you set the IP address to, as long as both the PC and the scope are part of the same subnetwork. This means that the first three numbers of the IP address must be the same and the last one must be different. In this case we're choosing 192.168.1.30. We then press Tab and click OK. There's also another way to access the Ethernet adapter settings. We can click on Utilities Setup and then on Show Windows Desktop. This allows us to enter the Windows menu of the scope, and we can just click on Control Panel, Network and Internet, and then Network and Sharing Center, and change adapter settings. Most PCs, and especially laptops, only have one Ethernet port. So how can we circumvent this problem? Well, there are devices available on the market which allow us to turn a USB port into a LAN port. And this is what we will be using here. The video shows one of these devices. As you can see, they're quite simple in construction, and you can just plug them in. They usually plug and play, and then a new network connection should appear on your list of network connections. We right click and change the name and call it LaCroix scope so that we can identify it easily. We then right click again, click on Properties, and we can then change the IP address of our Ethernet adapter, as we did before. We'll set the IP address to 192.168.1.20. Press Tab and then click OK. Now if we plug in a crossover cable into the LaCroix scope, make sure this is a crossover cable, and then we plug it in as well in our USB to Ethernet adapter, we can see that the cross over the LaCroix scope connection has disappeared, showing that the connection is now active. We can now go to the Start menu and select Run, then type CMD and OK. This allows us to go onto the command prompt, and we can then ping the scope with the IP address which we set for it. For those of you who are not familiar with the ping command, it just basically allows you to test a connection over LAN. So if we just type ping 192.168.1.30, which is the IP address we set for the LaCroix scope, we should get a response which indicates that the connection is active and working well, and data transfer can take place between the scope and the PC. If everything is working well, we should see something which resembles what's shown on the screen. So, now that the connection between the scope and the PC has been set up and verified, we're going to look into how to communicate with the instrument. First of all, we'll use the Agilent Connection Expert program, which will allow us to make the first communication with the instrument, send commands, read responses, and also to set up a unique address for the instrument, which we can then use in MATLAB. We initially click on Refresh All, which will refresh all the interfaces available on the PC, which are available for us to use. So Agilent Connection Expert has identified three interfaces on this PC: a COM port, a LAN interface, and also a USB interface. You may notice how there is a yellow circle next to the name of each interface, and that is because they have not yet been verified. The way we verify them is just by clicking on each one of them. like so. And you can see how a green tick appears once the interface has been verified. The one we're interested in is the LAN connection, because that's what we set up. So we just right-click and select Add Instrument. Now the instrument should be detected automatically, and indeed it is. However, I don't trust this method, it doesn't always work. So the best way to do it is to just click on the Add Address box and then type in the IP address manually. We know which IP address we set the scope to, so that should be no problem. We then click on Test Connection, and the program indeed confirms that the instrument is present. Then we can also click on Identify Instrument, and again we are told that it's a LaCroix oscilloscope, which is correct. We click on OK. And then the interface appears under the LAN interfaces. You can see that there is a visa address that's been assigned to it, and this is what we will be using in MATLAB to connect instrumentation. Now if we right-click on the instrument name and select Send Commands to the instrument, a little pop-up window opens up which allows us to send and receive commands. The default command is the IDN command, which allows us to identify the instrument. If we click on Send and Read, then the command will be sent to the instrument and a response read back, and we can see that the response is again correct. We close this window and we go back to the instrument details. We must select this visa address now and copy it into the clipboard so that we can then use it in MATLAB. So let's open MATLAB. And then there are two ways in which we can access the instrument control toolbox. We either click on the Start button, select Toolboxes, and then Instrument Control and Test and Measurement Tool, or we can simply type in the command prompt TM2 and press Enter. Now if we expand Instrument Objects and right-click on Interface Objects, create New Interface Object, then we can select the interface type as Visa, and you can see that the correct address is already there. But just to double check, we are just going to delete that and paste the one that we've got from the Agilent Connection Expert. We then click OK. Now under Interface Objects we can see the one that we've created. If we now click on the object, we get some more information about it, the visa address at the very top. And also we're told that the interface object is disconnected. If we click on Connect, however, we can then create the connection with the instrument. We can send a command from here, just as we did with the Agilent Connection Expert, and we can send the very same command, IDN. If we then click on Query, we send the data and we also read back the response. And as you can see, we're getting exactly the same result. So we can now see that with MATLAB, we can communicate and control our instrument. Now, if we click on the Session Log tab, we can see that MATLAB shows us the code that is used to connect to the instrument, and also the code that we've used to send the IDN instruction and read back the response. Let's maximize the window to give ourselves a bit more space. If I now disconnect the instrument, additional code will be written in the session log, which shows me how to do it. This is a very useful thing because it will allow us to then cut and paste code from here into our script, and once we've done that, we won't need to reopen the Test and Measurement toolbox every time. Now let's move on to device objects. Through interface objects we can send commands and read back responses. An interface object effectively represents the interface between the instrument and the PC, the channel through which we can send commands and through which we can also receive data back from the instrument. But in addition to interface objects, the MATLAB Instrument Control Toolbox also allows the user to communicate with their equipment without having a detailed knowledge of how the hardware interface operates. So without having a specific knowledge of the low-level commands which you need to send to the instrument to get the data back. This is made possible through specific driver files with the extension .mdd, which are used to create these device objects. These objects allow the user to configure and query an instrument without the knowledge of its specific command set. And the drivers that are used to create them are bespoke to each instrument or instrument series and contain the functions necessary to change the settings and write or read data from and to the instrument. So, let us now create a device object for our LaCroix scope. We just right-click on device objects, create new device object, and then a new pop-up window opens up. In this window we must select the correct driver and the correct interface object. The interface object is already set to the right thing, so all we need to do is find the right driver for the LaCroix scope. This driver is called LaCroix Basic Driver, and then we click OK. We can see now that under Device Objects, a new device object has appeared, which is the one we just created. If we click on it, on the right-hand side of the screen, we can see that a lot of information is displayed. Now we can see yet again that the instrument is not connected at the moment, but if we just click on Connect, our connection should be established. As you can see, the status has now been changed to Connected. If we now click on the Session Log tab, we can see the code that MATLAB has used to create this connection through a device object. As in the previous case, we can just copy and paste this code into a script, and we won't have to use the MATLAB instrument control toolbox to generate the code every time. If we now click on the Functions tab, we can see a list of functions which are available for us to use, and each function performs a different operation. If we scroll down to the waveform functions and click on Read Waveform, we can see that MATLAB shows us a syntax to execute this function. However, we may want to have a bit more information to understand how to use it. If we click on Show Help, this information is readily available. And we have a great deal of details as well as examples as to how to use it. As an input argument for the function, we can put channel 1, for instance, to specify that the waveform we want comes from channel 1. The output arguments, as shown in the help for the function, are the y data, the x data, the unit for the y data, the units for the x data, and also a header. If we now click on Execute, we can see that the function has been completed successfully and that the vectors that we requested have been acquired. However, we can't yet use them in MATLAB because they're not part of the workspace. But this is easily solved because we can just export them . And then if we go back to the MATLAB workspace, we can see that they're now listed in the workspace window and hence available to use and be processed. If we go back to the Test and Measurement tool now and look at the session log, we can see that additional code has appeared that shows exactly what code is necessary in a script form to perform the operation that we've just performed by using the instrument control toolbox. So there's 3 extra lines of code which allow us to acquire the waveform from channel 1. And again, we can just copy and paste this into a script and we won't need the instrument control toolbox every time. If we now click on the Properties tab, in this tab there are a number of parameters which are listed, and what we can do is change the settings of the scope through these various parameters. For example, if we look at the time base, we can see what time base the instrument is currently set to by clicking on Get. And then what we get back is a variable which indicates the time base the scope is set to currently. We can also click on Show Help, and this gives us some more information about that specific parameter and how to set it correctly. Again, going back to the session log, additional code has been added, which shows how to get the time-based value from the scope. If we go back to properties now, and again we stay on the time-based parameter, we can also change its value by simply selecting it from the box that's provided, and then by pressing set. And the toolbox tells us that the operation has been completed successfully. The session log, yet again, shows the code that's necessary to set the time base for the scope. We can now just click on disconnect, and again the correct code will appear in the session log for us to disconnect the instrument. We've seen how the MATLAB instrument control toolbox can be used to set up a connection between the PC and our instrument, and how we can communicate with our instruments in that we can send commands and read back responses. However, this should be a first step in the creation of our control routines and should just act as a facilitating tool. Once we've got the first steps set up through the control toolbox, we can then use the code that MATLAB has created in the session logs to set up our own scripts. And then we won't need to open the instrument control toolbox every time, but simply use the code that we've copied from the session logs and the additional code that we may add ourselves in order to fulfill the testing and control requirements for our project. We've looked at two different ways to control the instrumentation, through an interface object or through a device object. If there is a driver available to create a device object, this is definitely the simplest option, and I do recommend it since it simplifies the code and the work of the programmer greatly. It also makes it more legible so other people can open it and modify it and understand it much more easily. We will be using a device object in our script so that we can make the code more legible and simpler to understand. First of all, we'll go to the session log for the device object that we've created for the LaCroix scope. We'll select all the code that MATLAB has created and copy it into a blank script. Now, we won't need a couple of these commands, the ones to get and set the time base, so we can just select them and delete them. But what we want to do is add a command so that once we've acquired the waveform, we can then plot it in a MATLAB graph. This command is quite simple and it's just plot X and Y. I have inserted a couple of breakpoints in the script so that we can run the code line by line. The advantage of this approach is not just that we can verify the instructions one by one, but also that MATLAB allows us to hover over with the mouse on any of the variables or the objects and show us what the object or the variable is set to at that very point along the execution of the script. The first few lines are just the code to connect the instrument. We don't need to do anything about those, and MATLAB created them for us and they're fine as they are. Now, if I just hover over with the mouse on the device object, I get shown its current status, and it says that it's closed. It also gives me details about the object itself. Now that I've executed the next instruction, which is used to connect the device object, when I hover over with the mouse on it, I can see that the device object is now open. This is a way to verify that the connection has been successful. We then execute the 3 lines of code that MATLAB created when we acquired a waveform from channel 1. Of course, we can modify this code. For example, we can change the channel number from which we are acquiring the waveform. But for now, we'll leave it as it is. Once the acquisition is finished, again we can hover over with the mouse on the name of the variables, and we can see that there is actually data in them. So this allows us once again to verify that the acquisition has been successful. Next, we plot the data that we've acquired. a new figure opens up in MATLAB which shows exactly the same thing that's shown in the scope. This is a pulsed waveform, so there is an RF carrier inside every pulse, and then between the pulses we've got no signal. Now if we zoom in, which we can do by using the magnifying glass icon with a plus inside it, we can then see the actual carrier inside the pulse. The last thing that's left to do is execute the next instruction to disconnect the device object. You can see that at the moment it's open, but now that I've executed the disconnect function, it is closed. So, how do we connect a second instrument through an additional LAN connection? Well, the first thing is just the same as we did before. First of all, we must set up the additional LAN connection on the PC and the LAN connection on the new instrument in such a way that they have a static IP address where the first three-digit numbers are the same and the last one differs. For example, we can choose 192.167.1.30 for the instrument and 192.167.1.20 for the PC. We won't be showing these steps again since we've seen them before in the case of the LaCroix scope. Once we've set up the IP addresses in such a fashion, then we can open the command prompt and use the ping command from there to verify that the connection is actually functioning properly, as we did before. And again, as we did before, we then go to the Agilent Connection Expert program and right-click on the LAN interface. Make sure you don't create a new interface because there's no need for that. Under the very same interface where you've created the LaCroix instrument, right-click and select Add Instrument. The same window opens up and the instrument should be detected automatically, which it is. But as before, we just go to the Add Addresses tab, and since we know the IP address that we've set up for the instrument, we'll just insert that in the boxes and get the program to look for that specific IP address and the instrument connected through that. We can then test the connection and we see that the instrument is present, and then select an IDN query and identify the instrument. And this also shows that the instrument is the one that we've connected. Click on OK. And then we can see that under the interface section, we have two instruments now. One is the LaCroix scope and one is the Agilent scope. We then right-click on the Agilent scope, we select Send Commands to the instruments, and as before, we select IDN and Send and Read. And this again gives us the right response, showing that we can send and receive commands from the instrument. We can now copy the visa address for this instrument and then we open MATLAB. We type tmtool to open the instrument control toolbox. Then we right-click on Interface Objects, create New Interface Object. We select Visa as the interface type, and then we copy and paste the visa address in the address box and click OK. Now, as you can see, a new interface object has been created with the IP address of the instrument that we just connected, the Agilent scope. Now, if we click on it and then click on Connect, it looks like the connection has been successful. To verify this, we'll use the IDN command. So type in IDN and then query, and we can see that the response is correct. We then look at the session log, and again we can see that MATLAB has created the code for us to connect to the instrument. Now if we click on Disconnect, the code to disconnect this interface object is also created.